Hi, and welcome to one more video on an error analysis. And in this video, we're going to talk about how errors propagate. Specifically, we're looking at systematic errors. And we're going to talk about how they propagate through addition and subtraction, multiplication, division, multiplication by or division by an exact number, and then finally we're going to talk about exponents and powers. With the propagation of uncertainties involving in addition and subtraction of values, if you have two measurements with two uncertainties, well, let's say 4. Let's say you've got measured quantities W, X, Y, and Z. Those are 4 measurements. And you've got 4 uncertainties or absolute errors of dW, dx, dy, dz. To figure out the value of Q, which is the sum of and the subtraction of W, X, Y, and Z, just add them and subtract them and you get a value of Q. But your absolute uncertainty in Q would be simply the addition of all the absolute uncertainties. So that's your first rule for systematic errors. These are the worst errors that you can have. Let's take an example. We'll look at the perimeter of a polygon. We're going to figure out the perimeter. Basically, it's just adding up each side. So we've measured the sides, and each side has some error. And we've got errors of 1 inch, 2 inches, 3 inches, and 4 inches for different sides. The perimeter will just be our measurements added up. 61 and 87 and 49 and 101 gives you 298 inches. The absolute uncertainty, the worst possible error that you can have, is simply summing up the uncertainties. So when you sum up 1, 2, 3, and 4, you get 10 inches. So your answer is the perimeter is 298 inches plus or minus 10 inches because you're uncertain in 10 inches. Multiplication and division is a little bit different. If you have measurements of x, y, and z, and you've got absolute uncertainties of dx, dy, and dz, then when you multiply and divide x, y, and z to get q, you have to figure out the fractional uncertainties also. The uncertainty in x divided by the measurement of x, uncertainty in y divided by y, and the uncertainty in z divided by z. Those are your fractional uncertainties. And to get the total fractional uncertainty, you add up all of the fractional uncertainties for each one. Here's an example. We've got a rectangle, and we've got an error on one side of 1 inch and an error on the other side, uncertainty of 3 inches in these measurements. 5 plus or minus 1 inch and 9 plus or minus 3 inches. So the area, of course, of a rectangle is length times width. 5 times 9 gives you 45. The fractional uncertainties would be 3, your uncertainty in the one side divided by 9 gives you about 33%. And the uncertainty in the width is 1 divided by 5, which gives you about 20%. So your total fractional uncertainty would be about 53% or 0.53. Now that's your fractional uncertainty. To get the total uncertainty, you would have to multiply the fractional uncertainty by the total area. In other words, what percentage? You have to multiply the percentage times the total area. We figured out the fractional uncertainty was 0.53 or 53%. So multiply that by 45 and that gives you 24 square inches. So your answer would be 45 square inches plus or minus 24 square inches. And that's what we see right there. There are other ways to propagate uncertainties depending upon the type of mathematical functions. If you're multiplying or dividing by an exact number, let's say you measure some value x and your uncertainty is dx, your uncertainty in your measurement, and you need to multiply it by an exact number n, then the value, in other words, your answer would be n times x, and your uncertainty would be n times dx. Let's look at an example. Let's say that we're going to jump over 3 buses, just like Evel Knievel. And we measure the buses, and we're pretty sure they're about 45 feet, but we're uncertain in about half a foot in our measurement because we're not sure if we measure to the bumper or to the back of the bus or what. So we got a half a foot uncertainty in our measurements. So we know our bus length is 45 feet plus or minus a half a foot. If we want to jump over 3 buses, that means it's 135 feet. But there's some uncertainty in that measurement. What is the uncertainty? Multiply the total number of buses, 3, it's an exact number, times your uncertainty, a half a foot, and that gives you 1.5 foot error. Hopefully, it'll be shorter and not longer. So, in effect, the measurement that we have is 135 feet plus or minus 1.5 feet. If you measured consistently smaller, then you would have a measurement of 133.5 feet. If you consistently measured longer, it would be 136.5 feet. So it could be as small as 133.5 and as large as 136.5. So that's a pretty big range. And of course, you don't want to land short. And Evel Knievel died on December 1st, 2007. Thought I'd just throw that in there because he jumped buses. And then finally, we're going to look at how you handle exponents and powers. Let's say you have a value x that you measured, and it's raised to the n power, and you have absolute uncertainty of dx in it. That's your uncertainty in your measurement. Your fractional uncertainty would be what you normally calculate, dx over x, but then multiply it by the power, n. Here's an example. Let's say that you bring your paisans to the pizza parlor to get a large pie. And this pie is massive. It's 10 feet. You measure it to be 10 feet in radius. And you have some uncertainty because you're not sure if you're measuring out to the edge of the crust or the pepperoni or the cheese. So you have an error of 0.2 feet in your measurement. The total area of your pie is pi r squared. You know that pi is 3.14. Multiply that by 10 feet. And that 10 feet is raised to the second power. It's r squared. So that gives you a total square feet of that pie of 314 square feet. That's a lot of pie. The fractional uncertainty would be your error in your radius measurement. That's dr divided by the actual radius r. And dr we said was 0.2 and your radius was 10 feet, so that gives you about 2% error. Your total fractional uncertainty will be the 2% or 0.02 times the exponent, which is 2, which gives you 0.04. So your total uncertainty in the square footage of the pie is the pie's measurement, not measurement, but calculation of area, 314, multiplied by the total fractional uncertainty, which was about 4% error. So that gives you an absolute uncertainty of 12.5 square feet. So your answer for how much pi you have would be 314 square feet plus or minus 12.5 square feet. Wow, that's a lot of pi. Well, I hope you enjoyed this video. I'll talk to you later.